Good morning, everybody. I'm on the move, frustrating the video people, but it's good to see you. So we're into a whole new chapter, chapter 9, which is not going to be on this test on Tuesday, but it sure will be on the final exam. I always am a bit amused at the images that are on the first page of the chapters. Yeah. I feel like at the last minute, some marketing person came in and changed all those images to make them flashier or something, because they often don't really match with what's going on. For example, this is a beautiful sunset photo of the Very Large Array in New Mexico, but it's definitely not the radio telescope that Jocelyn Bell Burnell used to discover pulsar. In fact, this is it. I guess it's less photogenic. It was in a field outside Cambridge, UK. She just laid a bunch of wires out, and they were able to detect radio waves coming by and also figure out what direction it's coming from. And she spent the first 2 years of her PhD building it. Then she did all the data analysis. She discovered a pulsar. Let me find my notes here. First pulsar ever known. I guess it was a kind of a strange little signal. So it was. I think originally called it LGM for Little Green Men, because they thought it might be something like a signal from extraterrestrial intelligence or something. Turns out it's just to be a rapidly rotating neutron star. And so we're going to talk a little bit about conservation of angular momentum, which is what causes a star to spin a lot faster as it collapses. And it looks like we're doing rotating chair maybe on Friday, right? Okay, there we go. All right, I did promise we were going to do it. And then, of course, her supervisor is the one who won the Nobel Prize, so that was kind of a disappointment. Speaking of the term test 2, there's an age sheet, obviously, but so it's the same format. I try to keep the same format on the mini-term test, and both the term test, the final exam. You get a calculator, obviously. You need an age sheet that you prepare. So any equations that you don't feel like memorizing, just write them on your age sheet. That's the idea, because I'm not going to provide a formula sheet with all these equations. I think it's actually a good practice to, it's actually a bit of a learning experience to make up your own age sheet and write down these things. It solidifies it in your own head, I think, a bit. This is a good question. I'm 99% sure. I've booked this room, so I just need to find a TA to open and close the doors. But this Friday in one of the practicals rooms, the first practicals room on the right, from 5 to 8 p.m., there'll be some students from PhysU who are going to run in one of these help sessions, so hopefully that's helpful. I'm having trouble with my thingy here. Term test 2 age sheet. This comes from the Piazza. The question was, should you write the equations from chapters 1, 2, 3, and 4? And the answer is that I certainly won't be giving them to you, so yeah, write them. You have to, not me, but I guess the question is, would they be useful? All the questions on the term test are going to be from chapters 5, 6, 7, and 8, right? So, but I kind of think it is useful to have at least those kinematics equations, because they come up a lot. Like you have those two cars, they crash, stick together, and they skid a lot, and then they stop. Well, I always go back and use that 2ax minus x equals v squared minus v 0 squared. That equation seems to come up a lot, so it's a good one to have in your age sheet somewhere. Although I guess I've memorized it. It's better to write it down than to memorize, I think. I don't know if you can read this. A student was wondering if the elastic potential energy equation, which I can write out here, U of a spring. Do you remember if you have a spring that's compressed or stretched, there's an equilibrium position, and then there's X. And US it turns out to be 1/2 K times X squared. And this is always positive. It doesn't matter if X is negative or if X is positive. So I think a negative X might represent that you're compressing the spring, and a positive X might represent that you're stretching the spring. Doesn't matter. Either way, you've stored energy in that spring because it's not at equilibrium. So it's a parabola thing, and it's always positive. That was a great question. Okay, so this is problem set 7, question 1. This is one you have to submit. And the student was wondering how you get, so there's this equation for torque, which comes from your textbook. There's a plus or minus, depending if it's clockwise or counterclockwise. And then it's F times L times sine theta. And the question is, which one's the theta? Well, to me, what you have to do is draw, like let's say you've got a ladder, for example. just say, and if it's leaning against a wall, you can imagine a bunch of forces on it. There's going to be a normal force up here. There's going to be a normal force here. Normal, you call it normal 1 and normal 2 or something. There's going to be friction forces, maybe a static friction force like that. And then there's going to be this gravity, right, mg. And so if you set the axis of rotation to be down at the foot, which is fine. You have to define that, and I could define positive torques to be counterclockwise. Then the normal force N2 and the static friction, since they're acting at the axis of rotation, they don't have any torque. So it's only mg and n1, and then, so what you do is you have to connect these vectors tail to tail. So if you want to find the torque of n1, for example, then you use, this is that L vector. I think you would have to say, wasn't this 72 degrees or something? If this is L, and this is n1, and this is maybe 18 degrees or something, and this is 90 degrees, then I think that theta here is going to be 90 plus 18, so 108 degrees. So it's going to be N1 times L of the ladder times the sine of 108 degrees. Does that make sense? You should connect them tail to tail before you find the theta. That's the trick. Example. And it's going to be the same thing with mg. That'll be an L over 2 vector going up that way, and then your gravity is acting down. It's probably going to be greater than 90 again. It's going to be like 72 plus 90, I think. Okay. Term plus 2 content. Will we need to know uncertainties and how to calculate things like standard deviation on the upcoming test? Well, yes. To the first question, yes, uncertainties, but no, not standard deviation. So this was all on this thingy, experimental uncertainty. We've been using all semester in your practicals to figure out the plus or minuses on things. It's the weakest link rule. You want to do an example? I'm sure you guys have been doing this, but let's do one. Example. Test question on uncertainties. In practicals, you measure the displacement and time interval of a cart, and let's say for some reason it's not accelerating, you know that, so it's just going at constant speed, or constant velocity, I guess, and you measure that it goes a distance of 1.16 meters, plus or minus a centimeter, and you measure with a stopwatch that it's 1.6 seconds, but you think that your plus or minus on your stopwatch is about 0.2 seconds. And I think that comes from like your human reaction time, I think. Even though your stopwatch will display something to like a millisecond or whatever, I feel like when you press go and stop on a stopwatch, there's a much bigger than a millisecond plus or minus on that. So there's ways of estimating that. Somebody here has estimated it to be 0.2. But the question is, what's the uncertainty in the velocity or in the speed? And they even tell you the speed is 0.725 meters per second because they correctly determine the velocity. And the question could be, what should you report as the uncertainty? Well, just use, so there's that thing gives 3 steps. Step 1, which is determine the percent uncertainties. Step 2 is that find the weakest link and pick the weakest link. Step 2, identify the weakest link. I'm just taking right out of your PDF there. The weakest link. And then step 3 is going to be use that percent and times it by this velocity to give you your uncertainty in the calculated quantity. Determine the uncertainty in the calculated quantity. And it's very similar to what you would do in actual second-year physics labs. The only difference is that in later years, you'll actually combine the different percent uncertainties with the quadrature rule. You just add them in quadrature. Just take the squares of them, add them up, and take the square root. That'll give you that percent uncertainty. So step 2 is a bit different, but step 1 and step 3 are exactly what you would do even in upper year labs. So there's 2 things. There's displacement. It's 0.01, so 1 centimeter for every 1.16 is your measurement. So the percent uncertainty there is 0.8%, 0.086. And then the time interval, somebody estimated it to be 0.2 seconds, and you're measuring 1.6, and I got 12% for that. So that's your weakest link. So in this case, and if you do the quadrature sum, you'll still find 12% actually. In this case, it's the time interval. So use that 0.125 to get that the delta V is the 0.725 meters per second that you determined multiplied by 0.125. And then you get 0.091 meters per second. So what you would say, if you're measuring speed, is it's 0.725 plus or minus 0.091 meters per second. So that's a 9. Make sense? Yep. Good. Sorry, where's my thingy? No one will hear you if I don't give you the mic. Ready? This question.
Okay. What if you have multiple trials and you're finding an average velocity in the end? How do you do the uncertainty there?
So you find the velocity every time?
Mm-hmm.
Well then, yeah, you can just look at the scatter of the velocity measurements. You don't have to do any of this propagation stuff.
Okay.
So this is when, so you use this particular thing, weakest link, when you have the uncertainties of 2 quantities, and then you're using those, so you're stepping away from your experiment now, and you're using those to find a new quantity. So you're only measuring displacement and time in this case. That's a great question. You guys are going to be ready for this on Tuesday night? I'm hoping you've been doing this all semester, so you're good at it, so in the practicals. Okay. Put that there. What else is going on? Oh yeah, so I think we're doing this stuff. We've already done a bit of this stuff, so I'm a bit repeating. I tend to do kind of go over things more than once, and we get a little deeper each time, sort of like a spiral. I sort of go past it, but this time go a little farther. So this is just saying you've got some object which is rotating. This is the beginning of chapter 9, by the way. And it's going around, and there's 2 pieces of tape here. One is the orange piece of tape on the outer rim, and one is this yellow piece of tape, which is a little closer. Hopefully my video people are got me on the right spot. So, but basic idea is that the speed, so the angular speed, the amount of angle that these 2 pieces of tape sweep out in a certain amount of time is the same, because they both take the same amount of time to go around the whole circle. But the circumferences are not the same, right? So the speeds are not the same. The one on the outer edge is always going faster, more meters per second than the one in the middle, but it's same radians per second, right? So there are similarities between the motions of different points on a rotating body. During a particular time interval, all the objects will turn through the same angle delta theta. So that's where we do this arc length thing. S is r times theta. And then From that, we divide by delta t, and we go to omega. And again, I kind of have gone through this before, so I'm going through it a bit quickly. But the basic idea here is that this thing is called an omega. And it's not a W, even though it looks just like a W. And it's the limit as delta t goes to 0 of delta theta divided by delta t. It's the instantaneous, well, it's a slope, really. If you plot theta versus time, and it's going like this or something, then at some particular moment, you take a tangent, and that gives you omega versus time. Slope of tangent. So you can kind of imagine, I'm not going to try to draw it, but you could draw the slope of that, any tangent at any point, and do a graph of omega versus t. And then another way of turning that around, if you have uniform circular motion, you can find the delta theta by taking your omega times t. Okay, let's give you guys something to do. If you have a carnival with a Ferris wheel, so this is talking about comparing angular speed to tangential speed, where angular speed is measured in radians per second, and tangential speed is measured in meters per second. Okay. And so it's the two pieces of tape. You're saying compared with this, the seats on the outer rim, the one that I've circled there, the halfway to the edge, cars, I guess. How does their angular speed and tangential speed compare to the ones on the outside? I'll give you a minute to think about that. So a lot of you are saying same angular speed, but a smaller tangential speed, which is what I like as well. It's really good. 89%. So basic idea here is that V is the tangential speed in meters per second. And omega is the angular speed in radians per second. And since it's a solid object, I guess, omega, I guess I'll just say here, is the same, kind of by definition, for all points on a rotating rigid body. Because in the same amount of time, they'll all sweep out the same amount of angle in the same amount of angle. And so, and then the equation here is omega is equal to V is equal to omega times R. So, I guess the speed is 0 for points at the very, very center. They're not moving at all. They're just kind of turning around. And as you get farther and farther away from the axis, you get faster and faster. Okay. So angular velocity omega is the rate of change of angular position. The units are radians per second. Then the other thing that can happen is that you can have the rate of change of omega, and that's called alpha. Another Greek letter. And the units of alpha are radians per second squared. And it's the same thing. All points on a rotating rigid body have the same value of alpha as well. So you can't, when objects are rotating, can we still model them as point-like objects? No. We've gone beyond point-like objects now for these chapters 8 and 9. That's a bunch of little particles. And so what we can do is kind of put them all together and imagine them as being one object, which its center of mass might move, and also it might be rotating, and we kind of consider these two motions separately, the spinning part and the moving part. The moving part is when you can consider something like a point particle, but then if it's rotating at all, you have to consider that separately. And those are the three equations that you use a lot of the times. The distance that you travel is theta times r, and the The speed is omega times r, and the acceleration in meters per second squared is just alpha times r. So all you do is just times all these things by r. So this is what we had to do this morning on the pre-class quiz. A child is riding on a merry-go-round, and their father is pushing the merry-go-round so that it is speeding up. The distance of the child from the rotation axis is 1.5 meters, and omega is 2, and alpha is 1. So what's the tangential speed? Well, you just use tangential speed as omega times r. So it's 2. Now you got to use radians per second, because it's SI units, I guess, times 1.5, and you get 3 meters per second. That's how you do it. You guys got it? The next one was asking about the the AT. So same sort of thing. A sub t is equal to alpha times r. In this case, alpha is 1 times r is 1.5, and you get 1.5 meters per second squared. And then the fun one was this one, which was AR. So this one is a tricky one. It's v squared over r. Okay. The radial acceleration is always v squared over r. And so that's, you have to just know what the tangential velocity. But you from before, it was 3, right? Vt is equal to omega times r is 3 meters per second. So you just do 3 squared divided by 1.5. And I got, it's 9 over 1.5. I got 6 meters per second squared. Any questions about this pre-class quiz this morning? The third one was a bit tricky. Everybody's good? How are you doing up in the balcony? Balcony people, hi. Everybody's good up there. I would never be able to throw that high, but I did it once, but I'll never do it again. Okay, let's do a couple of top hat questions. Basic idea here is that we have this, I guess, historical convention. I think where it comes from, I'm always trying to remember, why the heck do we do counterclockwise the positive and clockwise the negative? And because it seems kind of stupid, but I think the reason was that if you measure that angle, theta, going from the x-axis up towards the y-axis, that's counterclockwise, I guess. So that's why they do that. But basically, this is how it all works out. There's speeding up, slowing down, and speeding up. And it's very similar to, remember, velocity and acceleration. If the velocity and the acceleration are in the same direction, that means something's speeding up. If the velocity and the acceleration are in opposite directions, that means the thing is slowing down. So similarly, if omega and alpha have the same sign, it could be plus plus or minus minus, then the rotation is getting more, speeding up. And then I guess if omega and alpha have opposite signs, then it's slowing down. Okay, so here's a fan, which is, you know that it's rotating clockwise. That's the way to tick, tick, tick of a clock. And you know that it's speeding up. So from those two pieces of information, use the historical convention. The counterclockwise is positive. What do you think are the answers here for sines of omega and sine of alpha? So think, pair, share. Please share with your neighbor. Yeah, omega is negative, and since it's speeding up, that means alpha and omega have to have the same sign. So that sucker is going clockwise and getting faster and faster. So also the alpha is clockwise. So that's great. What about this one? It's hard to see here. There it is. So now I've got the fan going counterclockwise, and it's slowing down. Hopefully you can kind of see it there. Give you a minute to... 92% said omega is positive, alpha is negative. Yeah, that's what I like. So, right. So if it's counterclockwise rotation, then you know right away omega is positive from that historical convention. And then it says that it's slowing down its rotation, so that means alpha is the opposite of omega. So that means it must be negative. Okay. Great job, guys. All right. Moving right along. So we're kind of summing up rotational kinematics, and then we're going to get into dynamics. But this is that analogy chart. Remember I tried to talk about this before, where you kind of just go to Greek. So in the linear side, like if you have 1D motion or something, x specifies position, and the SI units of x is meters. Well, and then I guess v is the slope of that. It's the slope of a v versus time, x versus time graph. V is the slope of x versus time, and that's going to give you meters per second, rise over run. And then the slope of a v versus time curve is called the acceleration. So your rise here will be in meters per second, and your run will be in seconds. So meters per second is meters per second squared. Well, it's the same thing with rotation. Theta now specifies that angular position that you're at, and if you make a plot of theta versus time and take the slope, that gives you omega in radians per second. So the SI unit of angle is the radian. And similar, if you take omega versus time and plot that and take the slope, you've got radians per second as your rise, your run is seconds, so you get radians per second squared. So some people may be a little concerned about a units check here. So radians are the magical unit because radians can disappear and reappear in equations as they please. And I think they're the only unit we use that's allowed to do this. So normally, if you have kilograms or something on one side, if they don't cancel, you can't just make them go away. But radians are the exception to that rule. They can go away. And for example, even this equation, the units don't make a lot of sense. If you look at it, units check. It's VT. You know that's in meters per second, right? So that's that side. This side is omega, which is in radians per second. And then we multiply it times the radius, which is in meters. Okay, so really it's radians times meters per second is the units. So what we do in physics is we cross that one out, and we say that it's meters per second. Okay. It just disappears. It's just like a leprechaun. It just goes poof, and it goes away. Don't usually do that with other units, but you can do it with radians, and you're allowed. It's a dimensionless unit, I guess, and that's why we use it. There's a math reason. It's something to do with circumference, right? But okay, let's move on here. These were those equations. There's a fourth equation. Do you remember I introduced the fourth one, which is v plus v0 over 2. The average speed is equal to x divided by t. Remember that? So there must be a similar one for rotation. What would it be? Well, instead of v's, we write omegas. So the average rotational speed, I guess, is going to be, instead of x's, we write thetas, divided by, and you still write time. So that's your fourth little equation, special one. So that can come up. What do we have here? What time is it? Let's do an example. A bicycle wheel has an initial angular velocity of 1.50 radians per second. And a constant angular acceleration of alpha is equal to 0.2 radians per second squared. Through what angle has the wheel turned between t equals 0 and t equals 2.5 seconds? So what I'm kind of imagining here is that maybe you've got this bike wheel or something, and maybe it starts off at here, I guess initial. We could put theta 0 or something like that. And then it goes turning around like that. So this little piece of tape ends up over here. Starts there and then goes there. And what's happening is that it starts with some initial angular velocity, and it looks like it's speeding up because they're both positive. So what you do is, what else do we know? That alpha is constant. So we can use the equation of constant angular acceleration. So what we're going to do is go back here. There's all these different equations. The difference is that each one of these equations doesn't contain something, either the final velocity or the position or something like that. So what the heck are we doing here? So we need to find theta. So that's important. So we basically here we have omega 0 and we have alpha. And we have, t. T is 2.5 seconds. We have t, and we need theta. So we don't care about something, right? I'm confused here. What do we not care about? Pardon? Why? 9.6. Oh, yeah. That's it. Yeah. Don't care about omega final. Yeah. Or just omega in these equations. So let's use, I like it. Thank you. So let's use equation 9.6. Good idea. So, and that is that, let's look at it again. Theta, so it's that thing you've already got. Theta is 0 plus omega 0 t plus 1/2 alpha t squared, which we can almost do in our sleep, right? So, did we have theta 0? Maybe what we'll do is assume, because it's just asking for the change, theta 0 equals 0. So theta is going to be 0 plus 1.5 times 2.5 plus 1/2 times 0.2 times 2.5 squared. Is that great? So I put that all in and I got 4.37 on my calculator. But does anyone know the units? It's radians. Yeah, very good. It's not degrees. You just plug in the SI unit that you like, which is it's got to be radians. So that's actually, it turns out that this is less than a full turn. A full turn would be 2 pi radians. 2 pi radians. So around 6.24 would be a full turn. Okay. So good? Questions on that one? All right. The other thing that happens with these is that these equations of constant acceleration is that sometimes they come up when something's rolling without slipping. So what's interesting is that if something's going along the floor like that, then whatever the tangential speed is, if it was in the axis sort of reference frame, that turns out to be what the speed of the car is, or the axle, if it's rolling without slipping. So these equations are the exact same equations we wrote down just for what the tangential speed and tangential acceleration was for points on the rim. I'm just using capital R now because now it's the radius of the wheel, I guess. So you want to find out how fast your car is going, you get your omega for your wheels, multiply it times the radius of the wheel, and that gives you that speed. Some great questions from this morning. Somebody asked, rotation acceleration depends on the net torque. So now we're getting into dynamics. Does that mean that the rotational acceleration depends on both the magnitude of the force in a direction and the place that it exerts on the arm? That's exactly right. The greater the net torque on some object, the faster alpha is. That's called Newton's second law for rotation. And there's another thing, it's not mass, but there's going to be rotational inertia. The other question is, since radians per second is a standard unit of angular velocity, are we allowed to express angular velocity in degrees per second? Well, yes, you definitely can. That's also right. But if you're going to use those equations, yes, but be aware the SI unit of omega is radians per second. So if some of these equations on your aid sheet only work if you express omega in radians per second. So it's safest, I think, to just convert to radians if you have degrees. For example, this VT is omega r. You can't plug in degrees there, you'll be off by a factor of 57. Okay. So thanks for those great questions this morning. Let's plate this baby. So we're getting now into why things rotate, and I have a little demo that Jonathan set up. And so it's a plastic bar with some masses that you can slide in and out. So, for example, if I put them right at the very center, and then see if it's easier to rotate it turns out to be extremely easy to rotate. I can sort of spin it, and it's just made of plastic, and so it's very easy to twist its direction or to accelerate it. But if I take that exact same object, same masses, and now move them to the outside, then all of a sudden, it's completely different. It's actually difficult to spin it up. It wants to, if it's rotating now, it wants to continue rotating. And it takes a lot of force to slow it down. And what Jonathan was saying, he was imagine you're shoveling snow with a shovel, and you try to lift up a bunch of snow this way. Well, it's going to take a lot of force somehow to do it. But if you somehow pick up the snow, hold the snow part of the handle in your hand, and just try to rotate the handle, that is going to be very easy. And the difference here is what's called rotational inertia. It has to do with the mass, but also how far the mass is from the rotation axis. So this is large rotational inertia, and then I can take the same mass, move them towards the center, and now I've got a small rotational inertia. And it's very, very easy to just change its omega. Okay. So rotational inertia depends on the mass of an object and also the distribution of mass around an axis of rotation. So the greater the distance between an object's mass concentration and its rotation axis, the greater the rotational inertia. So there is a crazy-looking equation which they talk about here. We consider a body that's made of n particles, each of mass m sub I, where I is some index number, and each particle is located at a distance r sub I from the axis of rotation. So we had defined a new number here, which is called rotational inertia, I. I don't know why it's called I, but it's, again, we're running out of letters here. It's got units of kilograms meters squared. You sum up all the particles' masses and multiply them times that particle's distance from the rotation axis squared. So, example. We're going to do an example on top hat. Just start it up, actually. Actually, I got time for it. I do. For example, if you have if n equals 2, if there's two particles, then the equation looks like this. It's m1 times r1 squared plus m2 times r2 squared. So we are going to consider two dumbbells. One is, and they're both, what they are is two masses that are connected by a massless rod, like a very light plastic rod or something with two larger masses. So you neglect the mass of the rod here. So there the distance is capital R, and the masses are little m. That's dumbbell A. Dumbbell B is a different object that has half as much mass, but twice the distance between the two masses. So think and pair up. Share your answer, please, with your neighbor. Give you a minute to click on that one, please. And then we'll work it out. 89% are voting for dumbbell B, which is also what I like, but I don't think it's all that obvious. I think you have to sort of check it, right? So the way I would check this is I would say M1, so let's call these 1 and 2, and 1 and 2. So for this dumbbell A, if the rotation axis is at the center, then you've got m times r over 2 squared, plus the other one, m times r over 2 squared. So you just have to work that out. I think it's going to be 2m times r to the squared divided by 4. So it's going to be mr squared over 2. And for B, similar thing, but this now is the distance r to each one of them. So I've got m over 2 times r squared plus the other one, m over 2 times r squared. So this is just equals mr squared. So I guess, yeah, that's half. So IB is greater than IA by a factor of 2. So great work, everybody. So what's the point of all of this stuff? Well, this is where we're heading with all this for Chapter 9, is we had all this kinematics we've been working on all day today. Now we're doing dynamics, which is, for linear things, the force and the mass determine the acceleration using Newton's second law, which is acceleration in the x direction, in meters per second squared, equals that force, the net force, divided by the mass. So we've got an analogous thing going on. The analogy to force is torque. And we know all about torque from Chapter 8. And the analogy to mass for rotation is this rotational inertia. So different objects have different rotational inertia. In kilogram meters squared, you take alpha is equal to the net torque divided by I. And that's your analogous Newton's second law for rotation. So great job today. Something to think about for next time. What if the pulley on this hanging mass system was not massless? So what if it has a rotational inertia? Is the tension in the string the same? And if not, which tension is larger? We'll talk about this on Friday. So I'll see you then. Okay, yep.